Okay, looks like we have got some viewers now with us. So welcome everyone again. I was saying at the start, maybe at that time, not everyone was logged in, that this review session is really about what you guys want to cover. We'll cover as many topics as you are interested in or whatever questions you are interested in. And once you run out of questions, then we'll end this review session. And since this is the first time I'm doing a review session on Hangouts, there may be a few glitches. So please bear with me and let me know if there is anything that I can do to smooth this process. I already have gotten a few questions that I'll try to address. If you guys come up with more questions, please use the Q&A section. I prefer that. Rather than using the events page where I see one question at least posted, but it's not very easy for me to go back and forth. Okay, so I'm going to start with the first question, which is the first question that's asked is that it says, I'm a bit confused as to how to go from the continuous time signal x of t to a discrete time sequence x of n. Can we go through homework problem 3.63? So let me go through that homework problem. And for that, I will share the screen here. And we'll go over this thing. So problem 3.63 it's given that you have a continuous time signal xa of t, which is equal to 3 sine 32 pi t minus 2 cosine of 24 pi t plus 4 sine 120 pi t plus 8 cosine of 144 pi t. And the question is asking that this signal is sampled at a sampling rate of 40 hertz. And you're asked to write the expression for x of n. Now, the person who asked this question was wondering that they understand how graphically sampling works, but how do you do this analysis? So whether you are looking at it graphically or mathematically, sampling is basically the process which says that if you have a signal xa of t or ga of t or any other variable that you use for that, you basically measure its value, measure or record its value every capital T second. This is the case when you are doing uniform pointwise sampling, which is the case for this class. So all we have to do is figure out what are the values, and in this case where our signal has a closed form expression, we can come up with a closed form expression for our samples. So we are given the sampling rate is 40 hertz. This means that my sampling time is 1 over 40, or you can just call it capital T, TS, doesn't matter. And my xn is literally defined as xa of nt, where n takes any possible value. So all I do is replace little by nt. So I get 3 sine of 32 pi n, and t is 40, so n by 40 minus 2 cosine of 24 pi over n by 40 plus 4 sine of 120 pi times n by 40 plus 8 cosine of 144 pi times n by 40. And after that, it's just simple calculations. I get 32 divided by 40, that's 8 by 5, or there's 4 by 5. So it's 4 by 5. I have here, again, it's 6 by 10, or 3 by 5 again. And similarly, you can do all these simplifications, and at the end of the day, I'll just write this down. This is 3 sine 4 by 5 pi n. That's the first expression that you get, minus 2 cosine of 3 by 5 pi n plus 4 sine of 3 pi n plus 8. So this will be 72, 20. I can do again, this is 36, 10, 18, 5. So this is by 5. Now you can simplify it further if you are interested, and if you leave it at this point, you have it most of the problem done, but we know that sine of 3 pi n is always 0. You can also try to write it in terms of the principal frequencies. So you know 18, 5 pi is bigger than pi, so you can try to write that as a value between minus pi and pi. And that's an approach that you can do to write it in a more shorter form. But if you don't end up doing that, even in this case, I'll be happy to see that answer. So it's really a case of where you have a signal where you are doing basically you are given a closed form expression, and you are able to write that closed form expression by simply replacing little t by n times capital T. So I hope this addresses the question, the problem that was asked. If it does not, I'll be happy to go over it. So people who ask this question, if they can let me know over the events page by a comment that they are satisfied with the answer, then we'll move on to the next question. So the next question that I've been asked is, could I go over question 2E from the 2014 midterm? So let me go to the 2014 midterm and see what that says, and look at that problem. So it is about 2E. Okay. I'm pulling it up. I'll share it on the screen also, so that everyone can see that question if they don't have access to it. So let me just do that. Okay. So I'm sharing it on the screen. This is the question that was asked. Question 2 is about consider a continuous time signal x of t. It's 3 cosine 8,000 pi t plus 2 sine 12,000 pi t plus cosine 16,000 pi t. You are given the sampling period of this signal, and you obtain a discrete time signal. Now, after that, you are told that you reconstruct a new signal using sinc interpolation as follows. So you're given the sinc interpolation formula. And what you are asked in 2A is sketch and label the continuous time Fourier transform of x hat of t and mathematically express x of t in terms of continuous time cosine and sine functions. So we'll go over that problem. Okay, so let's go to the screen. Okay, so this is 2014 midterm, and the problem is 2E. Now, if during the discussion you get confused, feel free to pose that as a follow-up question. I'll be happy to take it up, okay? So the first thing that you are told is this question is really about you are given a signal x of t, and you are asked that you are sampling that signal with some time period t to get x of n. And after that, you are actually not doing any processing. After that, you are told that you use it. So this is used to construct x hat of t using sinc interpolation. Now, the terminology may sound strange to you, but sinc interpolation, if you remember exactly, is nothing. If you have the right sinc interpolation formula, which is what is given in the question, if you have the right sinc interpolation formula, x hat of t, which is equal to summation n from minus infinity to infinity, x of n, sinc of pi t minus nt, or where sinc means sine pi t minus nt over pi t minus nt. This is just a code word for saying that actually you are taking your sequence xn and you are passing it through a discrete to continuous converter t to get x hat n, and the discrete to continuous converter, this is made up of an ideal reconstruction filter. Okay. So first of all, what is happening in this question is you are starting with a continuous time signal. You are ideally sampling it, and after sampling, you are then ideally reconstructing it. So signal, you start from the signal, sample it, and then immediately reconstruct it. There are only two things that can happen in that case if you are doing ideal sampling and ideal reconstruction. One thing is that you satisfy the Nyquist criterion, and in that case, what you get at the output is what you input into the system. So the first condition is if we satisfy the Nyquist criterion, what is that criterion? That your sampling frequency 2 pi over t must be greater than twice the maximum frequency in your signal. If we satisfy that, then this means that x hat of t equal to x of t without any question. Why? Because we are doing ideal sampling, ideal reconstruction, sync interpolation with the right parameters. The same t is used at the sampling, the same t is used for sync interpolation. We should get back x of t. Or the second case that can happen is if we don't satisfy the Nyquist criterion, then what happens? We know that the reconstructed signal will have aliasing. And what does aliasing do? That it just maps higher frequencies that are above the maximum frequency your system can handle. So if your sampling frequency in radians per second is fs, then your system, so I'm right now talking about in hertz. If your sampling frequency is fs hertz, your system can handle maximum frequency must be less than fs over 2, or we will have aliasing. So of course, right now I haven't discussed the problem at all. I'm just trying to give you an intuition about what is this problem trying to ask. You are either going to get exactly the same input as the same output as the input, or you are going to get an aliased version. So let's first figure out, do we have aliasing or not? Okay, so we'll go over the part. So our x of t is 3. So this is what we are given. Our x of t is 3 cosine of 8,000 pi t plus 2 sine of 12,000 pi t plus cosine of 16,000 pi t. So we have one cosine which is 4 kilohertz. We have a sine which is 6 kilohertz. And we have a cosine which is 8 kilohertz. You can stay with the radians per second, that's fine too. Okay, and now sampling time is given as capital T is given as 1 over 6,000 seconds. What does this mean? That my sampling frequency is 6,000 hertz, i.e. it's 6 kilohertz. So if my sampling frequency is 6 kilohertz, the question is, do I belong to the first case, this one, or do I belong to the second case, the aliasing one? And the answer is that, so if my sampling frequency is 6 kilohertz, system can handle only 3 kilohertz maximum frequency. But all of my frequencies are above 3 kilohertz. So this means I actually belong to the aliasing case. Okay. Now, to figure out what aliasing is doing to our system, so we of course have a general understanding of where different frequencies are going to be mapped. This is my input signal. Okay. And we have a general sense of where our input frequencies are going to be mapped. There are many ways of doing this problem. You can either solve it using the aliasing plot that we had showed you in the class. Another way of doing this problem, which is what naturally follows, if you are actually doing the other parts of your problem, you naturally get the answer that you can simply go through those problems and end up getting. You will see that all of your frequencies will get mapped to actually 2 kilohertz. Okay? So you can use that as an aliasing chart, or you could just do it step by step using that formula that we have seen. So one way of looking at is we can look at the XPT signal, which is, we had defined it as the impulse sample signal, X of t times S of t. And we know what the Fourier transform of this thing looks like. XP of j omega has a Fourier transform of 1 over t, summation k from minus infinity to infinity, x of j omega minus k omega t, or k times 2 pi over t. Okay. And you can then try to plot it and go through the analysis, but it can become a little bit cumbersome. An easiest way is just look at where are the frequencies going to get mapped to using the aliasing plot that we had shown earlier. So this was the aliasing, if you remember your aliasing plot. The mapping is that up to your half of sampling frequency, so 3 kilohertz, the output frequency is exactly the same. At 6 kilohertz, your output frequency is 0. At 9 kilohertz, this is the input, and it keeps on going. Okay. So you could ask that if you are at a 4 kilohertz frequency, so you are in this region, and at 3 kilohertz, the output is 3. Now you come down 1 kilohertz, 4 kilohertz, your output is going to be 2 kilohertz. Now so this is for the 4 kilohertz frequency. The second frequency is 6 kilohertz. The 6 kilohertz frequency is going to get mapped to 0. Okay. So this actually frequency will become 0. And this 8 kilohertz frequency is, you are 6 plus 2, you come to this point, and that is again 2 kilohertz. So what you get is 3 cosine of, so your output is going to be x hat of t is going to be 3 cosine of 2 kilohertz, that's 4000 pi t, plus cosine of 2 kilohertz, which is 4000 pi t, which is equal to 4 cosine of 4000 pi t. Okay. What I was really looking for in this question is, can you understand that you will have aliasing? And then when you have pure cosines and sines, can you understand that the aliased version is simply given by this aliasing chart where you can just read off the values? So I hope this addresses the question. If there is any follow-up question, I'll be happy to take that. Otherwise, let me know if it addresses. You can get a comment. Otherwise, I'll move on to the next question. Okay, so So the person who asked this question, can you let me know if this helps, or you would like me to spend more time doing this discussion? So I'll right now mark it as done, and then based upon what I hear back, I'll be happy to go back to it. Okay. I have two other questions, which are, let me read them. Okay, so one is, can you go over how to do part D on recitation quiz number 2 for section 2? Okay, we'll have to find out recitation quiz number 2, section 2. Let me go there. It's I'm just pulling up the file. Okay, so this is the question I've selected. Part D on recitation quiz number 2, section 2. So part D is, let me just share that so that everyone can see it. Let's see, where is it? Okay. So part D is, consider the discrete time signal xn is equal to cosine of pi by 4n plus sine pi by 2n. That is input to a discrete LTI system. We are interested in ensuring that the output of the LTI system yn is cosine pi by 4n plus pi by 2. Express this condition in terms of an equivalent condition on the frequency response of the system. Okay, so let's look at this. So this is recitation quiz. This was given to section 2, and it's part D that I've been asked to go over. And what you are here, the problem is really about understanding the role of LTI systems, discrete time LTI systems. You already understand that role for continuous time LTI systems. Here you are given a discrete time LTI system. The input of that system is xn, the output is yn. And the LTI system, of course, is described by its impulse response, or equivalently its frequency response h of e to the j omega. Now, the most important thing to understand for LTI systems is that LTI systems just do two main things to the input frequency. So LTI systems, the best way to understand is through their actions on the input frequencies. And what are the common actions that happen? That the output frequency, so if you are focused on, let's say, some frequencies, fix a frequency omega, little omega naught. Right? Little omega naught could be any number, let's say pi 4. Then the output frequency at omega naught of course, a frequency has a phase and an amplitude. So output frequency at omega naught is going to be affected by the Fourier transform of your impulse response or the frequency response. The output magnitude of frequency is going to be multiplied with the magnitude of the input frequency, magnitude of input frequency at omega naught, times what is the magnitude of the frequency response at omega naught. Magnitude of h of e to the j omega at omega naught. Okay. So we write this expression as y of e to the j omega equal to x of e to the j omega times h of e to the j omega. Now this formula you can use when you have an arbitrary signal, but if your input signal is a sinusoid, then the solution becomes much easier, because you know that a sinusoid that is input into a signal comes out as a sinusoid. The only thing that changes is the magnitude of that sinusoid changes, and of course the phase of frequency at omega naught in the output, that is equal to the phase in input at omega naught, right, plus phase in h of e to the j omega at omega naught. So that is what this question is really about. Do you understand the input-output relation of the LTI systems? So the input that you are given is xn equals to, so now just doing the basic review of the concept, you have input that is xn equals cosine of 4 pi by 4n plus sine of pi by 2n. And you are told that the output is yn equals cosine of pi by 4n plus pi by 2. Okay. Now, whenever you are given this, it's best to express this in complex sinusoids so that you can talk about frequencies, positive, negative, individual frequencies. So I'll write xn using the Euler's identity, that is equal to e to the j pi by 4n plus e to the minus j pi by 4n, and this is divided by 2, plus, again, use the Euler's identity here. I have e to the j pi by 2n times 2j minus e to the minus j pi by 2n divided by 2j. So this is my input. At the input, I have 4 frequencies. I have omega naught equal to pi by 4. I have minus omega naught, which is equal to minus pi by 4. This is due to the cosine. Then I have omega 1, which is pi by 2. And then I have minus omega 1, which is minus pi by 2. I have 4 frequencies at the input. And all of these frequencies have 0 phases. Right? There is no phase associated with these frequencies. If they had a phase, then I would have something like, for example, e to the j pi by 4n plus, let's say, pi by 2, right? That's my phase, e to the j pi by 2 times e to the j pi by 4n. So my phase is pi by 2. But in this case, I have 0 phase. Now, what's the output? Again, you have to write the output yn in terms of the Euler's identity. So you write that it's e to the j pi by 4n plus pi by 2 over 2 plus e to the minus j pi by 4n minus pi by 2 over 2. So what is happening at the output? I have only omega naught equal to pi by 4 and minus omega naught equal to minus pi by 4. In addition, I have the phase of omega naught is pi by 2, and the phase of minus omega naught is minus pi by 2. So what has my LTI system done? It has, so my LTI system, I had 4 frequencies coming into the system, but I'm getting out only 2 frequencies. How can that happen? The only way that can happen is if my h of e to the j pi by 2, the absolute value was equal to 0. Because if I have at the output, I have no frequency at pi by 2, this means that we have y of e to the j pi by 2 equals to 0, but x of e to the j pi by 2 is not equal to 0. So the only way that my output frequency at pi by 2 could be 0 is if my at pi by 2 my frequency response is 0. Similarly at minus pi by 2. So I must make sure that e to the minus j pi by 2 absolute value is also 0. We don't care about the phase because when you have 0 magnitude, the phase is indeterminate. Okay. Now, the output of this frequency pi by 4 is the same frequency with the same magnitude, but with a phase shift. Similarly, for minus pi by 4 over 2, I have the same output, but with another magnitude. So the next condition with another phase. So the next condition I get using that fact is that h of e to the j pi by 4, the absolute value of that must be equal to 1. Otherwise, you would not get the same magnitude frequency. Similarly, for the negative frequency, I should have e to the minus j pi by 4. The absolute value of that should be 1. Now, what about the phases at these locations? So at the output, we see that there is a phase shift of pi by 2 associated with the frequency pi by 4, and a phase shift of minus pi by 2 associated with the frequency minus pi by 4. So what that means is that my phase of h e to the j pi by 4, that must be equal to pi by 2. And my phase of h e to the minus j pi by 4 must be equal to minus pi by 2. Okay. Now, it's of course taken us a long time, but if you know your concept well, it's actually very straightforward to see. You convert your signals, if they are pure sinusoids, in complex exponentials. You figure out what is the output frequencies, and then based upon that, you can tell what are the conditions that you need on your frequency response. If a frequency has been killed, then your frequency response better be 0 at that frequency. If your output frequency amplitude has been scaled, then your frequency response amplitude should be proportional to that scaling. And the phase shift corresponds to the phase shift that your frequency response must have at that frequency. So I hope that addresses the question. Again, I'm going to mark it as done. If there is still some confusion, you can write me a comment on the events page, and I'll go over it again, or you can write address another question. Okay, so let's go to next question. I have 2 more questions on my list. If you have more, please put them up. Let me read for the frequency shifting property of the DTFT. So let me put that up. For the frequency shifting property of the DTFT, I recall you saying in lecture that this causes a frequency shift to the right and left of original signal. In problem 3.42, there is a shift omega plus pi by 5, and the original signal is only shifted to the left. Okay, I don't fully understand the question, so I'll have to go to the problem and see if I can better decipher it. A sequence for zero phase as sketched in this sketch, the DTFT of the sequence xn e to the minus j pi n by 5, that this causes a frequency shift to the left and the right. Okay, I'm not so sure what does it mean by the fact that it causes frequency shift to the left and the right, but probably go over this solution, and hopefully that will clarify. But if it doesn't, or if I'm having a little bit of a hard time understanding, please feel free to comment further, and we'll talk about it. So it's 3.42, I believe it's homework 2. Let me go to that. Okay. Okay, so the problem that we are given, I'll just switch to this. I'll just switch to the screen sharing mode. Okay, so we are given the problem. This is problem 3.42. The problem is saying you are given x of e to the j omega. It's actually plotted. The plot looks like the following. At 0, it goes up to pi by 2. This is pi. So this, and then you have from minus 2 pi by 3 to minus pi by 3. And you are given a new signal. So this is the Fourier transform of xn. You are given a new signal, let's call that Zn. So Zn is xn e to the minus j pi n by 5. Okay. Now this is what's known as the modulation property that we had done. We are effectively multiplying this xn, and this is a common operation that goes on in communication systems. We are multiplying our signal with an exponential with a frequency of pi by 5. So our omega naught is pi by 5 to get Zn. Okay. So this is the frequency shifting property that we had studied, that if you multiply your signal xn with e to the minus j omega naught n, then what it does is, if you go and look at table, let me just find out that the table of the DTFT properties. Let's see. Trying to find that table number. Okay, so it's table 3.4, and the property is frequency shifting property. So if you use that property, what you get is it's going to be x of e to the j omega plus omega naught. So our omega naught is, sorry, my omega naught is, so in this case, my omega naught is pi by 5. So what this means is that the whole spectrum will be shifted to the left by an amount of pi by 5. Okay. So what is going to happen is that this spectrum that you have is going to get shifted to the left according to this property. So this is just the shifting. You are doing shifting in frequency. So this point, instead of 0, it will move to minus pi by 5 because you are shifting everything to the left. Okay. This will become pi by 2 minus pi by 5. This minus pi by 3 point will become minus pi by 5 minus pi by 3. And this point will become minus 2 pi by 3 minus pi by 5. So I think what you might be referring to now that I've solved the problem is perhaps you might be talking about if we multiply with a cosine, because if you multiply it with just one complex exponential, this is the frequency shifting property. There is no other property. I might have misspoke about something. I don't remember, but this is the solution that you will get. If you have any, okay, I think I probably was sharing the wrong thing. So let me see. Okay. I was supposed to share this. I was doing this exercise, but shared the wrong thing. So what I was trying to say was that you are given this Fourier transform formula. You are just given the plot. You know that your original signal is xn. We call our new signal zn. And the operation is you are multiplying your xn with a pure complex sinusoid, which has a frequency of minus pi by 5. And if I do that, then in table 3.4 of your book, we have this frequency shifting property that is given here. Okay. What this means is that if you multiply something with a complex sinusoid, your spectrum just gets shifted either to the right or the left, depending upon the value of the frequency. So in this case, our frequency is negative, it gets shifted to the left. Okay. And that's then the answer we get, and there is no other answer to that. So as I said, I might have misspoke about something. If that's the case, I'll be happy to explain it further, but this is the right answer. Yeah. So let me know if this doesn't help. I'll be happy to go over it again. Okay, right now I'm marking it as done. Let's see if there are any comments that people are interested in. So, okay, I have a couple of other questions. One is, can you explain graphical convolution technique, flip and slide, as seen in question 4 of the 2012 midterm? If you could show how convolving ramp triangle with pulse rectangle would work, that would be great. So the question, the graphical convolution, in reality, this is a topic that we were supposed to cover in 345, but and one of the common things that is done in 345 is that you basically convolve two rectangular pulses. So it's about discrete time convolution. Or maybe it's continuous time. I have to go and take a look. So this is, the problem is question 4 of 2012 midterm. So let me go there. Question 4 of 2012 midterm. Okay, so I just opened up the midterm. I'm just going over the question 4. Okay, so this is actually continuous time convolution, which is again something that you guys have done many times in your 345 lecture. One of the common things that, one of the few things that you should remember in this class from 345 are some of these tricks, right? One of the tricks is, for example, when we convolve, again, I'm just using this opportunity to convey some of the basic ideas that you may have. When we convolve two signals in continuous time, right? If length of one signal of, let's say, x1n, x1t, so let's call it y of t is x1t convolved with x2 of t. If I convolve that, then length of y of t is equal to length of x of 1 of t plus length of x2 of t. That is one thing that you should always remember. If you convolve two signals, the output signal has a length which is the summation of the length of the two signals. This is for continuous time. Now, in discrete time, if I say yn is x1 of n convolved with x2 of n, then this was a homework problem. Length of yn in that case is length of x1 of n. So length of one sequence plus the length of the other sequence minus 1. Okay, minus 1 is discrete factor. So those are two things. Some other things, for example, is inverse Fourier transform of, so what is the impulse response of an ideal low pass filter or a box filter? That's another thing that you guys should remember. So if you are given, for example, a Fourier transform of h of j omega equals, let's say, 1 and 0, so up to omega less than or equal to pi by t, and 0 otherwise, you can replace pi by t by omega c. Then the inverse Fourier transform of that is a sinc function. It's sine pi t over capital T divided by pi t. And that is why the impulse response of the ideal reconstruction filter has an additional capital T factor here, because the height of the ideal reconstruction filter is capital D. So those are two of the things that, some of the things. Now the other thing to remember is that if you convolve, so which is this question that I'm coming to, convolution of this box function with itself is a rectangle, is a triangle, okay? And seeing that is not that difficult. So let's say the height of this is A, okay? And let's call that minus B to B without loss of generality. So what are the values of these things? We can figure that out. The way to do that is, if you don't remember, is using the convolution formula directly. So you have convolution of minus infinity to infinity, x of tau. So it's x of tau and x of t minus tau. You have d tau, okay? Now, your x of tau, so your x of t is simply, I'm doing it in the time domain, by the way. It doesn't matter what variable you use. I am doing it in the time domain. It says it's a for t between minus b and 0 otherwise, okay? So I just replace these limits because I know that x of tau is 0 beyond the limits of minus b to b. So I get x of tau. I can just x of tau, x of t minus tau d tau. And then I can replace minus b with a function a. Okay. And then I have x of t minus tau d tau. So I can take the a outside, minus b to b, x of t minus tau d tau. Okay. Now, I can replace this again. So what this is saying is that for every value of t that I am interested in evaluating my function, I simply I simply flip it by tau and then shift it by an amount t. Okay. So there are two cases that you can consider. One is when you flip it and you go to the negative side. First of all, let's look at what is the height of this thing, okay? What is the height of this triangle? So the height of this triangle corresponds to actually at t equals 0. So at t equal to 0, what is the height at y of 0? I have a minus b to b, x of minus tau d tau. Now if I flip x of tau around 0, so this is my 0, I get back the same thing. So I get a times minus b to b, and I have value of a times d tau. Okay. So all I get is a squared times 2b, which is 2a squared b. So the height gets multiplied. It's just the area of the gets multiplied, and then you just are looking at the area. Okay. Because when you are effectively just when you have tau equal to 0, you just have the two rectangles, two boxes sitting on top of each other. So the height becomes a squared, and they are going from minus b to b. So that is the height of this triangle, 2a squared b. Okay. Now, as far as figuring out where these endpoints are going to be, you can use You can go through it formally, or you can also try to use the fact that the length of this whole thing is actually going to be using the above formula. The length of this whole output sequence is going to be one sequence plus the length of the other sequence. So this is going to be 4b. So this endpoint is going to be at minus 2b, and this endpoint is going to be at 2b. Okay. And so then you can further figure out whether this is really a straight line or not. These two endpoints, whether this is really a straight line or not, by dividing your case into t is less than 0 versus t is bigger than 0. Okay. So for t less than 0, y of t is going to be a minus b to b x of t minus tau d tau. Now, when I flip this, so what is this saying? That you flip it, you flip x of tau. So when I flip my x of tau, I still get the same signal, minus b to b with a height of a. And now I'm shifting it to the left by an amount t. Right? So t is less than 0, so I'm shifting it to the left. So this is what I get. So the length of this thing is proportional. So now my area that I am covering, this is my area that I am covering. It is still, so I get a from minus b to minus t, because this point is minus t. And the value that I get is a, so that's d tau. Okay. So I get a squared tau minus t minus b. And so that's a squared b. So that's minus t plus b, or b minus t. Okay. So that's your value as for t less than 0. And similarly, you can do it for t greater than 0. Now, I understand that this is a long problem. But again, this is one of the things that you should remember from 345. I'm not expecting you to repeat this in this class. But if you even can remember some of the basic facts, that it looks like a triangle when you convolve two box signals, and the height of that is going to be when they are on top of each other, and the endpoints are minus 2b to 2b, you should be doing fine. So I hope that addresses some part of the question. Again, if you are not fully satisfied, or if you have further questions, I'll be happy to go over it further. Okay, right now I'm going to mark it as done, and you can let me know what your feedback is on this. Okay. Okay. Looks like we are running out of questions. So the last question I have, and if I don't get any, then I'll just conclude with a few main points. So it says, can you explain in question 3A, part 3 of the 2012 exam, how you found the sketch for magnitude and phase of h of e to the j omega? So question 3A, part 3, 2012. Let me just go there. Question 3A, part 3. Okay. So let me just share the question for those who don't have it. Okay, so this is a question about cascade of two LTI systems. Of course, you already know what LTS. If you understand what how to express the LTS system in frequency domain, then it's a simple, straightforward solution. But 3a part 3a is saying that you are given the first system's frequency response, h1 of e to the j omega, and you are given the second system's impulse response. And what you are asked in the first two parts is to compute the frequency response of the overall system, which is from end to end. And once you do that, then it is asking you to sketch and label the magnitude and the phase. So the question is about how did we find the magnitude and the phase. So I won't go into the details of part 1 and 2. What ends up happening is that the expression that you get is h of e to the j omega. This is the expression you get. Let me write that expression down. So okay, so this is midterm 2012, question 3A3. So I presume that the question is not about how we got h of e to the j omega. So h of e to the j omega, after doing the multiplication, we found out that that is equal to 0 for absolute value of omega less than or equal to pi by 8. It's 4 e to the minus j2 omega for pi by 8 is less than absolute value of omega is less than or equal to pi by 4. And it's 0 for between pi by 4 and pi. And then, of course, it repeats itself. Okay? So the question is asking to plot the magnitude and the phase. So first of all, to compute the magnitude and the phase, you compute the magnitude first. Okay? So of course, the magnitude of 0 is 0, so we get back 0 in that range. Now, what's the magnitude of 4 e to the j2 omega? If it was a complex number, then our life will be more difficult. We'll have to first write it in either the phasor notation, or we'll have to compute its magnitude. But in this case, it's really simple. It is given in the form, so a complex number c, which is given in the form r e to the j theta, where r is a positive number. You can verify that the magnitude of that is simply equal to r, and the phase of that complex number is simply equal to theta. Right? So that's just basic complex analysis. So the magnitude of that is 4 for pi by 8 between, so omega between pi by 8 and pi by 4, and of course the magnitude of 0 is 0. Okay. Now we are asked to compute the phase of e to the j omega. So we again look at the phase of these complex numbers. The phase of 0, we should really say actually that it's undefined, but you can write 0 if you want, or undefined, right? Because we don't care about the region where the magnitude is 0. So that's omega less than or equal to pi by 8. Okay, what's the phase of this? Again, using this notation, the phase of this is minus 2 omega for pi by 8 less than or equal to omega less than or equal to pi by 4. So the phase of your frequency response is, of course, a function of the frequency, and it's just by using this expression, r e to the j theta. My theta is minus 2 omega. And similarly, the end result is pi by 4, the phase is again 0 or undefined. Now you just have to plot it. So if I do the magnitude plot, this is the magnitude plot for pi by 8 to pi by 4 and minus pi by 4 minus pi by 8. Okay. So the height is 4. And the phase, it is a linear function for frequencies between pi by 8 and pi by 4. It's a line with a slope of -2. So it's a line with a slope of -2 here. What is the value at minus pi by 8? Its value is, so at minus pi by 8, the phase is -2 times minus pi by 8, so that is pi by 4. So this point is pi by 4. Okay. And at minus pi by 4, we'll have pi by 2 phase. So this is the phase. Similarly, in the range of pi by 8 to pi by 4, we have the same line. It's the same line with us, so it's just the same line. It goes up here, but I can't draw the line here because in this region the phase is undefined or 0. So I have to just draw. It's the same line, -2 omega. Right? But let me just color it just to make it clear. This is the line. It's the same slope. But in between, I have to cut off the line because in between it is 0. 0 due to this region. And again, if you want to find the values at pi by 8, the value is -2 times pi by 8. So it will be minus pi by 4. So this point will be minus pi by 4. And similarly, this point will be minus pi by 2. So I hope that explains the solution. I'm marking it as done. Again, if it doesn't work, please let me know, and I'll happy to go over it again. Okay, I've got a comment saying, can you explain the aliasing chart one more time? A couple of other questions, I'll go to that, but based upon what you guys said earlier, it's, can you explain the aliasing chart one more time? And another comment is, will all the work I did be posted? So if you guys want, I can post the scribbling that I've been doing on Sakai, and this video I'll leave it on YouTube for you to review later, but I'll then take it down after the midterm. Okay, so let me first answer the question of explaining the aliasing chart one more time. So let's go to the aliasing chart. Okay, so what is the aliasing chart? So aliasing chart is talking about how do continuous time frequencies. So remember, when we are talking how do continuous time frequencies map, if you take an input signal x of t, you sample it with a time period t, and then you do nothing else, but you just pass it through an ideal reconstruction again and get back x hat of t. What we know is that either you will get back the original signal, or you will have aliasing of the frequencies. Now, the best way to think of the aliasing is the folding phenomenon that we had looked at earlier. But if you are just talking about discrete frequencies, if you say I have a 4 kilohertz frequency, where does it get mapped to? The aliasing chart for positive, so there is a negative and a positive frequencies chart. Will just focus on the positive frequencies. So we'll take the example of specific values so that people don't get confused. So let's say the sampling frequency is 10 kilohertz. If you have a sampling frequency of 10 kilohertz, then the maximum frequency you can handle without aliasing is 5 kilohertz. So the aliasing chart is about if you input some frequencies, so you on the x-axis you have input frequency values, and on the y-axis you have the output frequency values. Okay, so when you do sampling, the maximum output frequency you can ever have is 1/2 of your sampling frequency. So this point is fixed at 5 kilohertz, 1/2 the sampling frequency. So fs over 2. And up to the 1/2 of your sampling frequency, fs over 2 or 5 kilohertz, the output frequency is exactly the same as the input frequency. This is supposed to be a straight line, so let me try it one more time. So the output frequency is exactly the same as the input frequency up to up to the 1/2 the sampling frequency. Okay, this is a straight line. Now, once you hit your input frequency hits 5 kilohertz, you cannot go any higher. Sorry, this should happen here. Okay, this is your output frequency. So once you hit 5 kilohertz, you cannot go any higher. My pen is right now deciding to really mess up, so I'll give it one more try. Okay. Now, once you go above 5 kilohertz, actually your higher frequency, so ideally you should have been able to go up, but you cannot. What happens is that you fold around this crease, okay, because you cannot go above half the sampling frequency. So at that point, actually, your output frequencies start decreasing. So much so that at your sampling frequency, and again, the relationship is just linear. So if you are, for example, so this is 10 kilohertz. If you are, for example, your input frequency is 7.5 kilohertz, then your output frequency is exactly 1/2 of this region. So it will be, since you have moved 2.5 kilohertz higher, you will come down 2.5 kilohertz. So your output frequency will be 5 kilohertz minus 2.5, that's 2.5 kilohertz. Okay. Now, once you hit fs, and if you go higher, then your output frequency starts going up again. And if you go higher, then it starts going down again. Okay. And all of these regions where it hits the maximum, all these regions are size of fs over 2. So no matter what input frequency you are given, you can always tell what is the output frequency by going through this chart. If this helps, please let me know. If it does not, also let me know, and I'll be happy to go over it one more time. Okay. Okay, so let's look at what other questions we've got. So, okay, so we are, the question is, I'll just select it. When aliasing results from sampling of a signal, will the height of the final aliased signal just be the addition of the heights of the two copies of the original signal? I think I sort of get the answer, but probably I don't fully. You will have the addition if you, so just going back to this plot that we had before, I was just doing the aliasing plot, right? So let's go back to that plot. Okay. So if your input frequency, this is, I think, a good example. If your input frequency was 7.5 kilohertz, your output frequency will be 2.5 kilohertz in this case, this example that I gave. And whatever is the magnitude of that frequency in this case will stay the same. The contribution of the frequency will stay the same. Now, if you already had a frequency at 2.5 kilohertz, if you already had a frequency at 2.5 kilohertz, then what will happen is that the strength of your 2.5 kilohertz frequency will be the strength of your original 2.5 kilohertz frequency plus the strength of the new frequency that folded onto it. Okay? So if you had, for example, let's say I had x of t equal to e to the j, let's say 5,000 pi t. So I had 2.5 kilohertz frequency plus e to the j, let's say, so let's say 15,000 pi t. After the aliasing, I will get back x hat of t will be the contribution due to this, plus this thing is going to get aliased into this also. So I'll have two contributions. So I'll get 2 e to the j 5,000 pi t. Okay? So it really depends what existed before at that frequency and what is the new frequency going to do there. So I hope that addresses the question. Okay, another question. The anti-aliasing filter, how do we determine its bounds? So the anti-aliasing filter, so what is the purpose of the anti-aliasing filter? The purpose of anti-aliasing filter is to remove all frequencies higher than the frequencies that your system can handle. So if my system has a sampling frequency of, let's say, 15,000, so my sampling frequency is 15,000 pi, which means it's, again, just take the example, it's 7.5 kilohertz, right? So the purpose of anti-aliasing filter is, let me pick a round number to make it easy. So let's make it 16,000 pi, so 8 kilohertz. Now, the purpose of anti-aliasing filter is to remove all the frequencies that are above what your system can handle. Now, if you have a frequency of sampling frequency of 16,000 pi radians per second, then the maximum frequency that we can handle is 1/2 of the sampling frequency. So it's omega t by 2, which is 8,000 pi radians per second or 4 kilohertz. So if my system can only handle frequencies up to 4 kilohertz, then I better remove all the frequencies that are above 4 kilohertz. So the bounds of an ideal anti-aliasing filter are always picked to be 1/2 of your sampling frequency. So your anti-aliasing filter ends up being an ideal low-pass filter. The height of that is 1. And the cutoff of that is, so you can write it, so this is, the cutoff is going to be 8,000 pi and negative side 8,000 pi. Okay. You can also, so remember, omega t is defined as 2 pi by t. So this means that omega t by 2 is pi by t. So sometimes we also write it as the cutoff is pi by t and minus pi by t. But it really comes from what is the maximum frequency my system can handle. And I want to remove all the other frequencies in the system. So I hope that addresses the question. Again, if there are comments or further clarifications, I'll be happy to go over them. I'm going to mark it as done. Okay. So looks like we are at the end of our questions. There is one other question that I have for the 2012 question. For the 2012 exam, question 2, can you quickly go over how they find the mathematical expression for D and E and how they got the graphs in B and C? Okay. So first, let's go to 2014 exam. Go to 2014. Just bear with me. I'll do that. Okay. And now the question is, so I've opened that. It's about question 2. Okay, so let's go to question 2. And quickly go over how to find the mathematical expressions for D and E. We already went over E. So you might have been late in joining. We already went over E. That was asked earlier. We actually went over some of the other details, but I'll quickly go over that. So how did it go for D and E, and how they got the graph in B and C? So B, C, D is what we want to do. Okay. So let me just share the question again so that people can remind themselves. Okay. So this is the question as we had discussed earlier. You are given 3 sinusoids, okay, 2 cosines and 1 sine. We are given a sampling frequency, and then just think in as I did at the class. There are only 2 cases that can happen in this case. You either do aliasing or you recover the signal exactly. Okay? So, but B is really about computing XP of j omega. So for that, we have to just remind ourselves what XP of j omega is. So let's go to this screen. Okay, so I'm just repeating the problem again for people who have joined in late. Part of that problem was we touched upon that at the very start of this discussion. So what you are given is an XT. You are doing sampling of that to get XN. And then you are passing it through an ideal reconstruction filter. That is what sync interpolation is, with the same time period to get X hat of T. And the first question we are asked is, what is xpj omega? So xp of we define xp of t as summation of n from -infinity to infinity, x of n, delta of t minus nt, and you are asked what is xp of j omega. Now this is something that we have done many times in the class. In class, xp of j omega, this is what we call the impulse sample signal, right? So this impulse sample signal is related to the Fourier transform of your input signal using three things. One is that you get a scaling of 1 over t. The other is you get multiple copies of your original Fourier transform. So the original Fourier transform, let's call the Fourier transform of this x of t as x of j omega. So the original Fourier transform is x of j omega, but we get multiple shifted copies of that. So that is k omega t. So this is a formula that we have gone over many times. Okay. And this is saying sketch and label the continuous time Fourier transform. So all we have to do for that is, first of all, compute the Fourier transform of my input signal. So I have 2 cosines and 1 sine. So my Fourier transform of this is going to be, so if you remember your cosine Fourier transform is, so if I have given cosine of omega naught t, the Fourier transform of that is an impulse of height of area pi at omega naught and an impulse of area pi at minus omega naught. This is something that you have to remember. This is one of the most fundamental facts in Fourier transform. Similarly, for sine, you have sine omega naught t. So that is, you have a height of area pi at omega naught. And I'm going to now be a little less rigorous and actually do this. I'll do this basically pi j and minus pi j, even though we shouldn't be drawing complex numbers on a real line. But just to give you a sense, this is effectively negative with a phase shift, but okay. So these are the Fourier transforms of your sines and cosines. So your input signal had 2 cosines with different magnitudes and 1 sine, and based upon that, you can write down the Fourier transform. You can figure out the Fourier transform of your input signal. So let me just go over that. So you will have basically, I just want to find the value. So you have a cosine of magnitude 3 at 8,000 pi. So at 8,000 pi, you have 3 pi cosine. At minus 8,000 pi, this is due to the cosine of 4 kilohertz frequency. Okay. Then you have another cosine at 16,000 pi, and its magnitude is 1. So I have another cosine at 16,000 pi and minus 16,000 pi. So this is, the area is of that is pi. And then I have a sine of 12,000 pi with strength of 2. So I get 12,000 pi, I get this 2 pi j. So I get 2 pi j at 12,000 pi. and then I get minus 2 pi j at minus 12,000 pi. And now doing the plot, it is simply, I am now, this is my main copy. So now I just have to write down this xp of j omega as you have multiple versions of this copy separated by multiples of omega t. Okay, and the 1 over t factor, now when you do 1 over t, so one of the things that you should be careful about, if you look at the solution, in the solution, so if you go and look at the solution, you will see that once you write down multiple copies of this, let me just switch to the solution so that you can see that. Okay. Okay, if you go to the solution, you see that what happens is your sign gets canceled. When you write down the multiple copies, your sign gets canceled. The area of each impulse gets divided by t, and some of you get 4 pi by t, because if you were to do that expression, you will realize that you have overlapping of impulses. So because of that, the way you get that is first write down your first main copy, then put down another main copy and figure out where the impulses will go. And what will happen is that the impulses will line up. For the sine case, they will get canceled. And for the cosine, you will get this figure that is shown in the solution. Okay. So I hope that answers about B. Okay, let's see what is. Okay. The C is sketch and label the discrete time Fourier transform x e to the j omega of xn. Now, to compute the x e to the j omega of xn, what you should really do is just compute xn from this formula x of t. Okay? So that is something that we had done at the start of the class. So let me go there. Okay. So at the start of the class, we had looked at, this is your x of t that is given in your problem. And if you replace, so what is your definition of xn? Your definition of xn is xn equals to x of nt. So if you want to compute the Fourier transform of xn, you first compute xn, which is this thing. Yeah. So this is your xn, and this is obtained by simply replacing little t by nt, and then doing some simplification. Once you get that, then you have expressions or discrete time expressions of cosines. The sign goes to 0, and then you can just use the property of what is the Fourier transform of your discrete time cosines. So that's how you get this solution that is given for part C of the problem. Okay. Now part D is simply asking, so if you just do this problem as it is, you see that the frequencies that you are getting to the two cosines are above the fundamental period. They are bigger than pi. So next part is asking, how do you represent those frequencies? What are the values of those frequencies within the minus pi to pi region? Again, a simple exercise, you know that they are periodic, so you subtract 2 pi from them and you get the values. Okay. So hopefully that answers. And then the last question we have already, as I said, done at the start. So well, so I guess that answers the question. I don't see any other questions posted. So I presume that means everyone is pretty satisfied or pretty ready for the session. I'll just remind you that the main things that you should know about in this exam are, of course, you cannot forget your knowledge of 345. But other than the sampling theory, one of the key things for you to remember is what is the effect of LTI systems in terms of frequencies? What do discrete time frequencies mean? When are the discrete time sinusoids periodic? What does sampling do to the input frequencies? What is aliasing, anti-aliasing filter, the ideal reconstruction filter? So those are the concepts. If you have further questions, since we are also, I guess, close to the end of the session anyways, if you have any questions, you can let me know. I'll try to address them. But other than that, I guess I will like to stop here because I don't see any further questions in the Q&A session. So I hope this was somewhat helpful, if not too much helpful. Remember, the exam is on Wednesday, so I'll see you all on Wednesday. Do go to your recitation sections. They will still be covering the previous exams, and see you all on Wednesday. Good luck.